Hello, and welcome to Bedside Physics. Before we settle in for tonight's journey through the universe, take a moment to like the video and subscribe if you enjoy calm, thoughtful explorations of science like this. It really helps the channel grow and allows more people to discover these quiet corners of physics. And while you're here, let me know in the comments where in the world you're watching or listening from tonight. Whether you're in a city apartment, a quiet countryside home, or somewhere halfway across the planet from where this video is being made, it's a gentle reminder of something fascinating. Wherever you are, the same laws of physics apply. The same cosmic rules that shape distant galaxies are shaping the space around you right now, including one particularly mysterious rule. A rule that says nothing, no spacecraft, no particle, no signal, can ever travel faster than light. It's a strange idea when you first hear it. After all, speed limits are something we usually associate with roads, vehicles, and traffic signs. They're imposed by governments or by the limits of technology. But the speed of light isn't like that. This limit wasn't designed, enforced, or invented. It appears to be woven directly into the structure of reality itself. Light travels through empty space at about 299,792 kilometers per second. That's fast enough to circle Earth more than 7 times in a single second. Fast enough to travel from the Moon to Earth in just over a second. And yet, according to everything we know about physics, that speed cannot be surpassed. Not by a rocket, not by a particle accelerator, not by anything with mass anywhere in the universe. Tonight, we're going to slowly explore why. We'll trace the story from the first scientists who tried to measure the speed of the light, to the strange experiments that puzzled 19th century physicists, to the quiet revolution sparked by Albert Einstein, when space and time themselves turned out to be far more flexible than anyone had imagined. Along the way, we'll encounter ideas that sound almost dreamlike at first. Clocks that tick at different speeds depending on how fast they move. Distances that shrink as objects approach light speed. Particles that must always travel at the same cosmic velocity. And a universe where the geometry of space-time itself quietly prevents anything from crossing this invisible boundary. We'll also wander into some of the more unusual corners of modern physics. Hypothetical particles that might move faster than light. Wormholes that could bend space-time like tunnels through the cosmos. Warp drives that attempt to move space itself instead of travelling through it. Some of these ideas are speculative, others are grounded in real mathematics, and a few sit somewhere in between. But each one helps illuminate the same deep question. Why does the universe seem to protect this one particular speed? Because the more physicists have studied the problem, the clearer something has become. The speed of light is not simply about light. It's not just a property of photons, lasers, or stars. Instead, it seems to be something much deeper, a limit connected to energy, information, causality, and the very geometry of spacetime itself. In other words, this cosmic speed limit may be less like a rule imposed on the universe, and more like a window into how the universe is built. So tonight, as we gently explore one of physics' most fascinating questions, you might begin to see this familiar number, 299,792 kilometers per second, in a slightly different way, not just as the speed of light, but as the quiet rhythm that helps hold the universe together. So get comfortable, settle in, and let's begin our journey into the physics of the ultimate speed limit, and why nothing can ever move faster than light. Somewhere in the quiet background of the universe, there appears to be a rule. Not a rule written in a book or enforced by any authority, but a rule that seems woven directly into the fabric of reality itself. Nothing can move faster than light. No spacecraft, no particle, no signal carrying information from one place to another. No matter how advanced our technology becomes, no matter how powerful our engines might one day be, the universe seems to insist on the same limit, a firm boundary that nothing with mass can cross. At first glance, this idea feels slightly strange. After all, speed limits are something we normally associate with human systems. Roads have speed limits. Machines have maximum operating speeds. Even animals have limits to how quickly they can run or fly. But in all of those cases, the limits exist because of practical constraints. Materials break, engines overheat, muscles tire. The cosmic speed limit appears to be something different entirely. It does not arise from engineering difficulty. It does not depend on technology. It does not even depend on what kind of object is moving. Instead, it appears to be built into the deep structure of the universe. The number itself is remarkably precise. In empty space, light travels at about 299,792 kilometers per second. That means a beam of light could circle the Earth more than 7 times in a single second. Another way to picture it is this. If you could somehow travel at the speed of light, you could move from the Earth to the Moon in just a little over 1 second, from the Earth to the Sun in about 8 minutes, and from our solar system to the nearest star in roughly 4 years. Even at these incredible speeds, however, the universe still stretches far beyond reach. The Milky Way galaxy alone is about 100,000 light-years across, meaning that even light itself takes 100,000 years to travel from one side of our galaxy to the other. Yet despite its astonishing speed, light does not appear to be merely fast. It appears to be the fastest speed that anything can ever reach, and that is where the mystery begins. For a long time, scientists did not suspect that this number had any deep significance. When the speed of light was first measured in the 17th century, it was simply understood as the speed at which light happened to travel. An interesting property of a familiar phenomenon. Early measurements were surprisingly clever. In the year 1676, the Danish astronomer Ole Rømer studied the motion of one of Jupiter's moons, called Io. By carefully observing the timing of Io's eclipses behind Jupiter, he noticed that the timing shifted slightly depending on whether the Earth was moving closer to Jupiter or farther away. The only reasonable explanation was that light itself took time to travel across space. This discovery revealed something important. Light did not move infinitely fast, as many people had assumed. Instead, it had a definite speed. Later experiments by scientists such as Hippolyte Fizeau and Léon Foucault refined these measurements during the 19th century, using rotating mirrors and precisely controlled apparatus. Their results gradually converged toward the same astonishing figure, a speed far beyond anything familiar in everyday life. At this stage, however, there was no reason to believe this speed had anything to do with the fundamental structure of reality. It was simply the speed of light. The deeper significance began to emerge when physicists started studying electricity and magnetism in the 19th century. One of the central figures in this story was the Scottish physicist James Clerk Maxwell. Maxwell developed a set of equations describing how electric fields and magnetic fields interact. These equations revealed something beautiful and unexpected. They predicted the existence of waves made purely from oscillating electric and magnetic fields. When Maxwell calculated the speed of these waves using known electrical constants, he obtained a value that matched the measured speed of light almost exactly. The conclusion was unavoidable. Light itself was an electromagnetic wave. This discovery was profound, but it also introduced a puzzle. Maxwell's equations seemed to imply that the speed of these electromagnetic waves was fixed. Not fixed relative to anything in particular, but fixed in an absolute sense. That idea made many physicists uncomfortable. In classical mechanics developed by Isaac Newton, speeds are always relative. If you throw a ball forward while standing still, the ball moves at one speed. If you throw the same ball forward while standing on a moving train, the speeds combine. From the perspective of someone standing beside the tracks, the ball's speed would simply be the speed of the train plus the speed of the throw. This simple addition of velocities worked beautifully for everyday motion, so physicists naturally expected the same principle to apply to light. If a flashlight was switched on inside a moving vehicle, surely the speed of the light beam should depend on how fast the vehicle itself was moving. And yet Maxwell's equations did not allow that. They seemed to insist that light always travelled at exactly the same speed. No matter how fast the source moved, no matter how fast the observer moved, this contradiction between classical mechanics and electromagnetic theory became one of the most intriguing puzzles in physics. Several brilliant scientists began exploring possible explanations. One of them was the Dutch physicist Hendrik Lorentz. Lorentz developed a mathematical framework describing how objects might change shape and time intervals might shift as they moved through space at very high speeds. His equations, now called Lorentz transformations, suggested that moving objects could experience changes in length and time in order to preserve the laws of electromagnetism. Around the same time, the French mathematician and philosopher Henri Poincaré was thinking deeply about the principles underlying physical laws. Poincaré proposed that the laws of physics should remain the same for all observers moving at constant speeds. This idea, known as the principle of relativity, hinted that nature might enforce certain universal constraints, yet even with these insights the full picture remained incomplete. Physicists were beginning to suspect that something unusual was happening when objects moved extremely fast. The familiar ideas of space and time that had guided science for centuries might not behave quite the way people expected. The speed of light, which had once seemed like a simple measurement, was gradually revealing itself as something far more profound. A number that appeared again and again in the equations of physics, a number that refused to change no matter how experiments were arranged, and perhaps most intriguingly of all, a number that seemed to mark a boundary in the universe itself. As the 19th century drew to a close, the stage was quietly being set for one of the most important discoveries in the history of science. A discovery that would show that the universe does indeed enforce a speed limit, not through force, not through resistance, but through the very nature of space and time themselves. The story of the universe's speed limit begins in a place that might seem surprisingly quiet and observational. Not in a particle accelerator, not in a physics laboratory filled with instruments and detectors. Instead, it begins with a telescope pointed toward Jupiter. In the late 17th century, astronomers were already carefully tracking the motions of the planets and their moons. One of the most dedicated observers was the Danish astronomer Ole Rømer, working in Paris in the year 1676. Rømer spent long nights watching the tiny moon Io as it orbited Jupiter. Io is one of the 4 large moons discovered earlier by Galileo Galilei, and it circles Jupiter with remarkable regularity, completing one orbit in about 42.5 hours. Because Io frequently passes into Jupiter's shadow, it periodically disappears from view and then reappears. These disappearances and reappearances occur with such regular timing that astronomers of the era treated them almost like a celestial clock. If the universe behaved in a perfectly simple way, those events would occur at precisely the same intervals every time. But Rømer noticed something peculiar. Sometimes the eclipses appeared slightly earlier than expected. At other times they appeared slightly later. At first glance the differences were subtle, only a matter of minutes. But the pattern was unmistakable. When Earth was moving toward Jupiter in its orbit around the Sun, the eclipses seemed to occur earlier. When Earth was moving away, the eclipses appeared delayed. Rømer realized that the explanation might not lie in the motion of Io at all. Instead, the delay could be caused by light itself taking time to travel through space. When Earth was farther from Jupiter, the light from Io had to cross a slightly greater distance before reaching the telescope. That additional distance meant additional travel time. The conclusion was remarkable. Light did not move infinitely fast. It had a finite speed. Rømer estimated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. His measurement was not perfectly accurate by modern standards, but the essential discovery was correct. Light required time to travel across space. This realization was one of the earliest hints that the universe contained speeds so enormous that they were difficult for the human mind to grasp. Over the next 2 centuries, scientists developed increasingly precise methods to measure that speed. In the 1840s, the French physicist Hippolyte Fizeau designed an ingenious apparatus that allowed the speed of light to be measured across a laboratory distance. Fizeau used a rapidly spinning toothed wheel and a beam of light that travelled several kilometres to a mirror and back again. As the wheel rotated, the returning light beam either passed through the gaps between the teeth or was blocked by the teeth themselves, depending on how long the round trip took. By carefully adjusting the rotation speed of the wheel, Fizeau could determine how long the light required to complete the journey. The result confirmed what Rømer had suggested centuries earlier. Light moved extremely fast, but not infinitely fast. Shortly afterward, another French physicist, Léon Foucault, refined the measurement further. Foucault replaced the rotating wheel with a rapidly spinning mirror, allowing much greater precision. His experiments showed that light travelled slightly slower in water than in air, confirming predictions from wave theory and providing further insight into the nature of light itself. By the middle of the 19th century, the speed of light had been measured with impressive accuracy. Yet at this stage, physicists still believed the speed belonged only to light itself. It was considered a property of waves moving through space, much like the speed of sound is a property of vibrations moving through air. Then a deeper pattern began to emerge. Several researchers studying electricity noticed something curious. In the 1850s, the German physicists Wilhelm Weber and Rudolf Kohlrausch conducted experiments measuring the relationship between electrical charge and electromagnetic forces. When they compared different systems of electrical measurement, they discovered a constant with the dimensions of speed. When that speed was calculated numerically, it turned out to be astonishingly close to the measured speed of light. This coincidence raised an intriguing possibility. Perhaps light itself was connected to electricity and magnetism. That possibility was soon confirmed by one of the most elegant theoretical achievements in the history of science. The Scottish physicist James Clerk Maxwell developed a set of equations describing how electric fields and magnetic fields interact with one another. Maxwell showed that changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. These relationships created the possibility of self-sustaining waves made entirely from oscillating electric and magnetic fields. When Maxwell calculated how fast those waves should move through empty space, he obtained a specific result. The speed depended on two measurable electrical properties of empty space: electric permittivity and magnetic permeability. Combining those quantities produced a value that matched the known speed of light. The implication was stunning. Light was not a mysterious substance or a separate phenomenon. Light was an electromagnetic wave. In Maxwell's theory, visible light, radio waves, and X-rays were all part of the same electromagnetic spectrum. They differed only in wavelength and frequency, not in their fundamental nature. But Maxwell's equations contained a detail that would soon become deeply puzzling. They predicted that electromagnetic waves travel at one specific speed, not a range of speeds, not speeds depending on the motion of the source, one exact value. If the equations were correct, then electromagnetic waves should always propagate through empty space at the same speed, regardless of how fast the source itself was moving. At first glance, that might not sound too strange, but it directly contradicted the everyday rules of motion described by classical mechanics. In ordinary situations, speeds combine through simple addition. If you walk forward inside a moving train, your speed relative to the ground is the speed of your walking plus the speed of the train. This rule works for almost everything in daily experience. So physicists expected light to behave the same way. If a lamp was switched on inside a moving vehicle, the light leaving that lamp should travel faster or slower, depending on the motion of the vehicle. Maxwell's equations, however, did not allow that. According to the mathematics, light would still move at exactly the same speed, whether the source was stationary or racing through space at tremendous velocity. This peculiar prediction raised an uncomfortable question. If the speed of light is always the same, then relative motion must somehow affect space and time themselves. At the time, many physicists assumed that light must be moving through some kind of invisible medium called the luminiferous ether. In that view, the constant speed predicted by Maxwell's equations would simply be the speed of electromagnetic waves moving through that medium. The Earth, moving through the ether, should therefore experience a kind of ether wind, similar to the breeze felt when riding a bicycle. Detecting that ether wind became one of the most important experimental challenges of the late 19th century, and solving that puzzle would eventually reveal something far more surprising than anyone had anticipated. The speed of light was not merely a feature of light, it was a fundamental property of the universe itself. Once physicists began to accept that light was an electromagnetic wave, a new question quietly emerged. If light is a wave, what exactly is waving? Sound waves move through air. Ocean waves move through water. Even waves travelling along a rope require the rope itself to exist. Every wave known to 19th century science needed a medium, some physical substance capable of vibrating. So it seemed natural to assume that light must also travel through something. That invisible something came to be known as the luminiferous ether. The idea of the ether was widely accepted throughout the 19th century. Physicists imagined it as a subtle, transparent medium filling all of space. It had to be present everywhere, even in the emptiest regions between stars and galaxies, because light from distant stars clearly reached Earth across enormous cosmic distances. At the same time, the ether could not behave like ordinary matter. Planets moved through space without any obvious resistance. If the ether existed, it had to be extraordinarily delicate, offering no drag on moving objects. In a sense, the ether was imagined as a strange combination of properties. It needed to be stiff enough to carry electromagnetic waves moving at enormous speeds. Yet it also had to be almost completely undetectable by ordinary means. Physicists of the era were comfortable with this idea because it seemed to match the behavior of waves in familiar materials. The ether simply became another background substance, like air or water, but more subtle and universal. Once the ether was accepted as real, an important consequence followed. If Earth was moving through this cosmic medium, then there should be a detectable motion relative to the ether itself. To picture the idea, imagine riding a bicycle through still air. Even on a calm day, you feel a breeze against your face. That breeze is caused by your motion through the air. The same principle should apply to Earth moving through the ether. As our planet travels through space along its orbit around the Sun at about 30 kilometers per second, it should experience what physicists called an ether wind. Light moving in the direction of this ether wind should behave slightly differently from light travelling across it or against it. In other words, the measured speed of light should vary depending on direction. According to classical mechanics, velocities simply add together. If a beam of light moved in the same direction as Earth's motion through the ether, its speed relative to an observer on Earth should be slightly different from light moving perpendicular to that motion. These differences were expected to be very small, but they should still be measurable with sufficiently precise instruments. Several scientists began exploring how the ether might behave in detail. One of the earliest proposals came from the French physicist Augustin Jean Fresnel, who was studying the behavior of light in transparent materials. Fresnel suggested that when light passed through a moving medium, such as glass or water, the ether inside that medium might be partially dragged along with it. This idea became known as the Fresnel ether drag hypothesis. According to Fresnel's theory, the ether might be partly carried along by matter, while still remaining mostly stationary on large scales. This partial dragging could explain some puzzling experimental observations involving the speed of light in moving substances. Although Fresnel's hypothesis solved certain problems, it raised new questions about how the ether interacted with matter. Another scientist who explored the consequences of ether theory was the Irish physicist George Fitzgerald. In the 1880s, Fitzgerald proposed a striking idea in response to the growing difficulty of detecting motion through the ether. He suggested that objects moving through the ether might physically contract in the direction of their motion. This effect, now known as the Fitzgerald contraction hypothesis, was originally introduced as a way to explain why experiments had trouble detecting the expected ether wind. If measuring instruments themselves shorten slightly when moving through the ether, that contraction might cancel out the differences scientists were trying to observe. At the time, the idea seemed unusual but mathematically plausible. Meanwhile, the Irish physicist Joseph Larmor developed detailed mathematical descriptions of how charged particles, which we now call electrons, might behave within ether theory. Larmor explored how electromagnetic fields and electron motion could produce transformations resembling changes in time and length. His work hinted at something extraordinary. The equations describing electromagnetic phenomena appeared to involve adjustments in space and time themselves. Even though Larmor interpreted these changes within the framework of ether theory, the mathematics was beginning to suggest that classical ideas about space and time might not be entirely correct. Still, most physicists of the era remained convinced that the ether must exist. After all, Maxwell's equations clearly described waves travelling through space, and waves, by every known example, required a medium. The challenge, therefore, was not whether the ether existed. The challenge was simply detecting it. As experimental techniques improved during the 19th century, physicists became increasingly confident that they would soon observe Earth's motion through this mysterious medium. The predicted effects were subtle but measurable. If Earth moved through the ether, the speed of light travelling along the direction of Earth's motion should differ slightly from the speed of light travelling across it. By carefully comparing these speeds, scientists believed they could determine both the existence of the ether and the direction of Earth's motion through it. The problem now became one of precision measurement. Instruments capable of detecting extremely tiny differences in the travel time of light needed to be designed. Experiments had to be arranged so that light beams could travel along different directions while maintaining exceptional accuracy. Physicists expected the ether wind to produce measurable shifts, perhaps small but unmistakable. By the late 19th century, the stage was set for one of the most famous experiments in the history of physics. an experiment designed specifically to detect the motion of Earth through the ether, and if the ether truly filled the universe as scientists believed, the evidence should appear clearly in the data. What happened instead would challenge the entire foundation of classical physics. The expected signal simply refused to appear. By the late 19th century, physicists were confident that the motion of Earth through the ether would soon be detected. The theory seemed clear, the predictions were precise, and experimental techniques had improved dramatically. All that remained was to perform the right experiment. Two American physicists, Albert Abraham Michelson and Edward Williams Morley, set out to do exactly that. Michelson was already known for his extraordinary skill in designing precise optical instruments, and his work focused on measuring extremely small differences in the behavior of light. In the year 1887, at what was then the Case School of Applied Science in Cleveland, Ohio, Michelson and Morley constructed one of the most sensitive devices ever built for measuring the speed of light. The instrument they used is called an interferometer. At its heart, the idea is elegant. A beam of light is split into two separate beams that travel along different paths. After travelling those paths, the beams are brought back together. When the two beams meet again, they form a pattern of light and dark stripes called interference fringes. These fringes arise because light behaves as a wave. When two waves combine, they can reinforce each other or cancel each other, depending on how their peaks and troughs align. If the two beams of light travel exactly the same distance in exactly the same time, the pattern remains stable. But if one beam takes even a tiny fraction longer than the other, the interference pattern shifts. Michelson realized that this technique could detect extraordinarily small changes in the travel time of light. Differences smaller than 1/1,000,000th of a second could produce visible shifts in the interference fringes. This made the interferometer an ideal tool for searching for the ether wind. The experiment was designed so that one beam of light travelled along the direction of Earth's motion through the ether, while the other beam travelled perpendicular to that motion. If Earth was moving through the ether at about 30 kilometers per second, the beam aligned with that motion should experience a slightly different effective speed compared with the beam travelling sideways. The difference would be extremely small, but Michelson's interferometer was sensitive enough to detect it. To ensure accuracy, the entire apparatus was mounted on a large stone slab floating in a pool of mercury. This clever design allowed the experiment to be rotated smoothly in different directions without introducing vibrations or distortions. As the apparatus rotated, the orientation of the light beams relative to the supposed ether wind would change. If the ether existed and Earth was moving through it, the interference pattern should shift as the instrument turned. The prediction from classical ether theory was clear. A measurable shift should appear. Michelson and Morley performed their experiment with extraordinary care. They repeated the measurements many times, rotating the instrument and observing the interference fringes under different orientations. And yet, something unexpected happened. Nothing changed. The interference pattern remained stubbornly stable. No matter how the instrument was rotated, no matter how carefully the data were examined, the expected shift simply refused to appear. This result became known as a null result, meaning the experiment failed to detect the effect it was specifically designed to measure. For physicists of the time, the outcome was deeply puzzling. If the ether existed and Earth was moving through it, the interferometer should have detected the ether wind, but it did not. Michelson himself initially suspected that experimental errors might be responsible. After all, detecting such a small effect required extraordinary precision. However, repeated measurements continued to produce the same result. The ether wind could not be detected. The implications were unsettling. Either Earth was somehow always stationary relative to the ether, which seemed implausible, or the entire concept of the ether might be flawed. Other scientists soon attempted to repeat and refine the experiment. One of the most persistent investigators was Dayton Miller, an American physicist who spent decades conducting ether drift experiments. Miller built larger interferometers and performed measurements at different times of year and at higher altitudes, hoping that subtle effects might reveal the motion through the ether. For many years, Miller believed he had detected small signals consistent with ether drift. However, later analysis showed that these results were most likely caused by temperature fluctuations and experimental noise rather than genuine physical effects. As experimental techniques improved throughout the early 20th century, increasingly sensitive measurements continued to confirm the same conclusion. The ether wind was nowhere to be found. The Michelson-Morley experiment had quietly revealed something remarkable. Light appeared to travel at the same speed in every direction, regardless of how Earth was moving through space. In classical physics, this behavior made little sense. If light were moving through a stationary medium, then motion through that medium should produce measurable differences in its speed. Yet the experiments insisted otherwise. This is one of the reasons null experiments are so powerful in science. When an expected effect fails to appear, the absence of a signal can be just as meaningful as a positive detection. In this case, the missing ether wind forced physicists to reconsider the assumptions underlying their theories. Sometimes the universe answers a question not with a discovery, but with silence. And that silence can be surprisingly informative. By the end of the 19th century, the situation had become increasingly uncomfortable for classical physics. The ether theory, which had seemed so natural and convincing, was struggling to explain the growing body of experimental evidence. The equations of electromagnetism worked beautifully. The experiments measuring the speed of light were reliable, but the framework used to interpret those results no longer fit together smoothly. Something in the foundations of physics needed to change. Within less than 2 decades, a young physicist working in a patent office in Switzerland would propose a radical idea that resolved the puzzle in an unexpected way. Instead of changing the behavior of light, he suggested that something far more fundamental might need to be reconsidered: the nature of space and the nature of time. At the beginning of the 20th century, physics found itself in an unusual position. The experimental evidence was reliable. The equations of electromagnetism developed by James Clerk Maxwell worked beautifully. Measurements of the speed of light were consistent and increasingly precise. And yet, the theoretical framework used to interpret these results was beginning to crack. Classical mechanics, developed by Isaac Newton more than 2 centuries earlier, had described motion with remarkable success. Planets, projectiles, pendulums, and machines all behaved exactly as Newton's laws predicted. But when light entered the picture, something no longer fit. Experiments like the Michelson-Morley interferometer suggested that the speed of light remained the same regardless of the motion of the observer or the source. According to classical ideas about velocity, that should not have been possible. Physicists had spent years trying to rescue the ether theory, with increasingly complicated explanations. Proposals such as the Fitzgerald contraction suggested that objects moving through the ether might shrink in length. Mathematical frameworks developed by Hendrik Lorentz described how time and space coordinates might transform in moving systems. These ideas were clever and mathematically sophisticated, but they still assumed that the ether existed as a hidden background medium. Then, in the year 1905, a young physicist named Albert Einstein approached the problem from a completely different direction. Einstein was not working at a large university laboratory. At the time, he held a position at the Swiss Patent Office in the city of Bern. His job involved evaluating applications for electrical devices, which left him with long stretches of time to think about theoretical physics. During that remarkable year, sometimes called Einstein's miracle year, he published several papers that would transform modern science. One of them carried the title On the Electrodynamics of Moving Bodies. In this paper, Einstein proposed a new way of thinking about motion, light, space, and time. Instead of trying to explain the strange behavior of light by modifying the properties of matter or inventing complicated interactions with the ether, Einstein started with 2 simple principles. The first principle was known as the principle of relativity. It states that the laws of physics are the same for all observers moving at constant velocity relative to one another. In other words, no experiment performed inside a smoothly moving system can reveal whether that system is truly at rest or simply moving at a constant speed. This idea had roots going back to Galileo Galilei in the 17th century. Galileo had already pointed out that passengers inside a smoothly sailing ship cannot determine their motion without looking outside. Einstein adopted this principle as a fundamental rule of nature. The second principle was even more striking. Einstein proposed that the speed of light in empty space has the same value for all observers, regardless of how fast the source of light or the observer themselves might be moving. In plain language, the speed of light is constant, not approximately constant, not constant only under certain conditions, constant for everyone. This statement seems simple at first, but it has astonishing consequences. If 2 observers moving at different speeds both measure the same speed for light, then something else must change to compensate. The ordinary rules for adding velocities can no longer apply. Einstein realized that the quantities which must adjust themselves are space and time. In everyday life, we tend to think of space as a fixed stage where events occur, while time flows steadily and uniformly everywhere. But according to Einstein's reasoning, those assumptions cannot hold if the speed of light truly remains constant. Instead, measurements of distance and measurements of time must depend on the motion of the observer. Clocks moving at high speeds run more slowly relative to stationary observers. Distances measured along the direction of a motion become shorter. Events that appear simultaneous to one observer may not appear simultaneous to another. These effects were not merely philosophical ideas. They emerged directly from the mathematics required to preserve the constant speed of light. Interestingly, the equations describing these transformations had already been written down by Hendrik Lorentz and explored mathematically by Joseph Larmor and Henri Poincaré. But Einstein took a bold conceptual step. He removed the ether entirely. In Einstein's theory, there was no need for an invisible medium filling space. Light did not require a background substance in order to propagate. Instead, the behavior of light revealed something about the structure of space-time itself. Space and time were not rigid and absolute. They formed a flexible framework that adjusted depending on relative motion. This idea would later be expressed elegantly by the mathematician Hermann Minkowski, who described space and time as part of a unified four-dimensional structure called space-time. But even before that geometric formulation appeared, Einstein's theory already contained the essential insight. The speed of light was not simply a property of light. It was a fundamental feature of the universe. Einstein's thinking was influenced by several philosophical ideas circulating at the time. One of the most important influences came from the Austrian physicist and philosopher Ernst Mach. Mach argued that scientific concepts should be grounded in observable phenomena rather than hypothetical entities that cannot be directly detected. His skepticism about absolute space and invisible mediums helped shape Einstein's willingness to abandon the ether altogether. Instead of inventing complicated explanations to preserve the ether theory, Einstein chose the simpler path. He assumed that the experimental results were telling the truth. Light travels at the same speed for all observers. Once that assumption was accepted, the consequences followed naturally. Other physicists quickly began exploring the implications of this new theory. The German physicist Max von Laue extended Einstein's ideas to additional areas of physics, showing how relativistic principles could be applied to electromagnetic radiation and high-energy processes. Within a few years, the new framework became known as special relativity. The word special refers to the fact that the theory deals with observers moving at constant velocities relative to one another without acceleration. Despite this limited scope, the theory fundamentally changed our understanding of motion. Speeds could no longer be combined using the simple arithmetic rules of classical mechanics. As objects moved faster and faster, approaching the speed of light, the transformations of space and time became increasingly dramatic. Most importantly, the equations of special relativity showed that the speed of light could never be exceeded by any object with mass. As an object accelerates toward this limit, the energy required to increase its speed grows rapidly. Pushing an object closer and closer to the speed of light becomes progressively more difficult. The universe itself appears to resist crossing that boundary. In this new framework, the cosmic speed limit emerges naturally from the structure of space-time. It does not require an invisible ether. It does not rely on mysterious forces. Instead, it arises from the way space and time are intertwined. Einstein's theory did not merely solve the puzzle posed by the Michelson-Morley experiment, it revealed something deeper. The universe contains a built-in limit to how fast information, energy, or matter can travel, and that limit is the speed of light. Once the two principles of special relativity are accepted, the universe begins to behave in ways that feel unfamiliar at first, yet follow perfectly clear mathematical rules. The first of Einstein's principles says that the laws of physics are the same for all observers, moving at constant velocity relative to one another. The second states that the speed of light in empty space is identical for every observer, regardless of their motion. Taken together, these ideas create a surprising conclusion. If the speed of light must always remain the same, then the measurements of space and the measurements of time cannot remain fixed. They must adapt. This adjustment appears through two remarkable phenomena known as time dilation and length contraction. Time dilation describes the way moving clocks appear to run more slowly when viewed from another reference frame. Length contraction refers to the shortening of distances measured along the direction of motion for objects moving at very high speeds. These effects are not optical illusions. They are not mistakes in measurement. They are real consequences of the geometry of space-time. To understand why, it helps to think about how different observers measure motion. Imagine two spacecraft passing one another in deep space. Each spacecraft carries its own clocks and measuring instruments. According to classical physics, both observers would measure time and distance in exactly the same way. Special relativity tells us something different. Each observer measures space and time using their own frame of reference. Because the speed of light must remain identical in both frames, the measurements of time intervals and spatial distances must adjust accordingly. The mathematics describing these adjustments had already been developed before Einstein's 1905 paper. The Dutch physicist Hendrik Lorentz derived equations showing how measurements of time and space transform between observers moving at different velocities. These equations are known as the Lorentz transformations. The Lorentz transformations reveal that as an object moves faster relative to an observer, time measured in the moving system appears to slow down. In clear language, a moving clock ticks more slowly. This effect can be described with a specific mathematical relation. In words, the relationship is expressed as time experienced by the moving clock equals the stationary time multiplied by the square root of 1 minus the square of the velocity divided by the square of the speed of light. Although that expression may sound complicated, the meaning is straightforward. When the velocity is small compared with the speed of light, the difference in time is extremely tiny. Everyday motions such as walking, driving, or even flying in an airplane produce effects far too small for humans to notice. However, as speeds approach a significant fraction of the speed of light, the difference becomes dramatic. If a spacecraft were traveling at 90% of the speed of light, time inside that spacecraft would pass noticeably more slowly compared with time for observers on Earth. A journey lasting 10 years for the astronauts might correspond to more than 20 years passing for people who remained behind. Length contraction works in a similar way. An object moving at extremely high speed appears shorter along the direction of its motion when measured by an external observer. The faster the motion, the stronger the contraction. At ordinary speeds, the change is imperceptible. A passenger train travelling across a landscape does not visibly shrink, but if that same train somehow accelerated to speeds approaching the speed of light, its length measured from the outside would become dramatically shorter. Both time dilation and length contraction arise directly from the requirement that the speed of light must remain constant in every frame of reference. The deeper explanation of these effects emerged soon after Einstein introduced special relativity. In 1908, the mathematician Hermann Minkowski, who had once been Einstein's professor, presented a powerful new interpretation of the theory. Minkowski suggested that space and time should not be treated as separate entities. Instead, they form a unified structure known as space-time. In Minkowski's formulation, every event in the universe has 4 coordinates. 3 describe position in space, and 1 describes position in time. Motion through the universe therefore becomes motion through this 4-dimensional geometry. Within this framework, the speed of light acts as a kind of conversion factor between spatial distances and temporal intervals. One of Minkowski's most famous statements captured the essence of the idea. He declared that space by itself and time by itself were fading away into mere shadows, and that only a union of the two would preserve independent reality. This geometric interpretation makes the effects of time dilation and length contraction easier to understand. Different observers moving relative to one another slice space-time into space and time in slightly different ways. Because of these different perspectives, they measure different intervals of time and different distances between events. Yet the underlying space-time structure remains consistent for all observers. For many years, these predictions of relativity seemed almost philosophical, because the required speeds were far beyond anything achievable with ordinary technology. But eventually experiments began confirming them with remarkable precision. One particularly elegant demonstration occurred in 1971, when physicists Joseph Hafeel and Richard Keating carried extremely precise atomic clocks aboard commercial airplanes. The clocks were flown around the world on eastbound and westbound flights, while identical clocks remained on the ground as references. After the journeys were complete, the airborne clocks showed measurable differences compared with the stationary clocks. These differences matched the predictions of relativity with impressive accuracy. Even more dramatic confirmations occur naturally in high-energy particle physics. At facilities such as the European Organisation for Nuclear Research, widely known as CERN, particles are accelerated to speeds extremely close to the speed of light. Certain unstable particles created in these accelerators normally decay after extremely short lifetimes when measured in their own rest frame. However, when these particles move at relativistic speeds, their internal clocks run more slowly relative to the laboratory frame. As a result, they survive much longer than expected. Particles that would normally exist for only a fraction of a microsecond can travel much farther through detectors before decaying, precisely because time dilation extends their lifetimes from the perspective of the laboratory. The closer an object approaches the speed of light, the stronger these relativistic effects become. Time slows, lengths shrink, energy requirements increase. All of these changes arise from the same underlying principle. The speed of light remains constant. To preserve that constant value, the universe allows space and time themselves to flex and adjust. What once seemed like rigid dimensions turn out to be dynamic parts of a deeper geometric structure. And within that structure, the cosmic speed limit begins to reveal itself not as a barrier imposed from outside, but as a natural feature of space-time itself. As physicists explored the consequences of special relativity more deeply, it gradually became clear that the strange effects of time dilation and length contraction were not isolated curiosities. They were hints pointing toward a new way of understanding the universe itself. The key step in this transformation came from the mathematician Hermann Minkowski, who recognized that Einstein's theory could be expressed elegantly using geometry. Minkowski suggested that space and time should no longer be treated as separate ingredients of reality. Instead, they form a single unified structure known as space-time. In everyday thinking, space is described by 3 dimensions. We use length, width, and height to specify the location of objects. Time, meanwhile, is treated as something entirely different. It flows continuously, marking the sequence of events. Minkowski realized that Einstein's theory naturally combines these ideas. Every event in the universe can be described using 4 coordinates. 3 describe where the event occurs in space, and 1 describes when it occurs in time. This 4-dimensional structure is what physicists call space-time. In this framework, motion through the universe is no longer simply movement across space as time passes. Instead, every object traces a path through space-time, sometimes called a world line. Even something sitting perfectly still on the surface of the Earth is not motionless in space-time. It is continuously moving forward through time. The geometry of this 4-dimensional structure contains the key to understanding the cosmic speed limit. Within space-time, events are separated not only by distance in space, but also by intervals in time. The relationship between these quantities determines how signals and objects can move between events. The structure of space-time introduces a powerful concept known as the light cone. Imagine choosing a specific event, such as a flash of light occurring at a particular place and moment. From that event, light spreads outward in every direction at the same speed. If we plot the possible paths of that light through space-time, the pattern forms a shape resembling a cone. The light emitted at that event creates a boundary. Inside this boundary lie all events that could be reached by signals traveling slower than light. Outside the boundary lie events that cannot be reached without exceeding the speed of light. This structure divides space-time into 3 regions. The future light cone contains all events that can be influenced by the original event through signals traveling at or below the speed of light. The past light cone contains all events that could have influenced the original event, and outside both cones lies a region where no signal traveling at or below the speed of light can establish a causal connection. This geometric picture provides a powerful way to understand the speed limit imposed by relativity. Nothing with mass can move faster than light because doing so would require leaving the interior of the light cone. Remaining inside the cone ensures that cause and effect remain properly ordered in time. Leaving the cone would disrupt that structure. The geometry of space-time itself forbids it. This geometric perspective also reveals why the speed of light is so special. In space-time diagrams, light travels exactly along the surface of the light cone. Massive objects move along paths that remain inside the cone. Their world lines always stay within this allowed region. Massless particles such as photons travel precisely along the boundary itself. Any motion faster than light would require crossing outside the cone entirely, entering a region of space-time where the familiar ordering of events could break down. The deeper significance of this geometry becomes clearer when viewed through the lens of mathematical symmetry. In the 19th century, the mathematician Felix Klein proposed an influential idea known as the Erlangen program. Klein suggested that different types of geometry could be understood by studying the symmetries that preserve their fundamental structures. For example, Euclidean geometry studies shapes and distances that remain unchanged under rotations and translations. Special relativity introduces a new type of symmetry known as Lorentz symmetry, which preserves the space-time interval between events. This symmetry lies at the heart of Minkowski spacetime. Transformations between observers moving at different velocities do not change the underlying spacetime interval. They simply alter how space and time are divided between observers. Because the speed of light appears in the equations defining this symmetry, it naturally becomes the invariant speed shared by all observers. The geometry itself demands it. Later in the 20th century, the British mathematical physicist Roger Penrose developed powerful visual tools for understanding spacetime structure. One of his contributions was the creation of causal diagrams, which map the relationships between events using light cones. Penrose diagrams compress the immense scales of the universe into manageable representations, making it easier to visualize how signals travel through spacetime. These diagrams reveal how light cones guide the flow of information and influence across the cosmos. Even across vast distances, the same geometric principles apply. Signals travel within the boundaries defined by light cones, and every interaction respects the same universal speed limit. The remarkable feature of this framework is that the speed limit does not arise from a force or a resistance. No barrier physically pushes objects back when they approach the speed of light. Instead, the limitation emerges from the geometry of spacetime itself. To exceed the speed of light would require an object's world line to tilt outside the light cone, but the equations governing spacetime simply do not allow such paths for objects with mass. The structure of the universe quietly prevents them. This geometric viewpoint also helps explain why the speed of light appears so consistently in the laws of physics. It is not merely the speed of a particular phenomenon, it is the speed that defines the structure of spacetime. Just as the shape of a sphere determines how straight lines behave on its surface, the geometry of spacetime determines how motion unfolds in the universe. Every particle, every signal, and every beam of light moves along paths shaped by that geometry, and woven into that structure is the quiet but absolute rule: nothing can outrun light itself. Another way to understand why nothing can travel faster than light comes from examining the relationship between energy and mass. Einstein's theory of special relativity did not only change our understanding of space and time, it also revealed a deep connection between matter and energy. One of the most famous results of this work appears in a remarkably compact relationship. Energy equals mass multiplied by the square of the speed of light. This statement is usually expressed as E equals mc squared, but the meaning is easier to appreciate when spoken clearly. It tells us that mass itself is a form of energy. Every object containing mass holds within it an enormous amount of energy simply by existing. The reason this amount is so large comes from the speed of light appearing squared in the equation. Because the speed of light is an extremely large number, multiplying it by itself produces an even larger value. Even a small amount of mass corresponds to an enormous amount of energy. This idea became dramatically clear during the 20th century through nuclear reactions. When tiny amounts of mass disappear during nuclear fission or nuclear fusion, the lost mass is converted into energy according to this relationship. The energy released in the core of the Sun, for example, arises because small fractions of mass are transformed into radiation through nuclear fusion. But the connection between mass and energy also plays an important role when objects move at very high speeds. In classical mechanics, kinetic energy increases smoothly as an object accelerates. If you push an object harder, it moves faster. In principle, there is no upper limit to how fast it can go. Relativity introduces a crucial modification. As an object moves faster and faster, its relativistic energy increases dramatically. The additional energy supplied to the object does not simply increase its speed in a straightforward way. Instead, more and more of that energy contributes to the object's relativistic inertia. The closer the object's velocity approaches the speed of light, the more energy is required to increase its speed by even a small amount. The mathematics describing this relationship appears in the relativistic energy formula. In clear language, the total energy of a moving object can be written as energy equals mass multiplied by the square of the speed of light divided by the square root of 1 minus the square of the velocity divided by the square of the speed of light. Although that expression may sound complex, the key idea is simple. As the velocity approaches the speed of light, the quantity in the denominator becomes smaller and smaller. That causes the energy required to accelerate the object to increase enormously. When the velocity reaches the speed of light itself, the denominator would become 0, and dividing by 0 leads to a quantity that grows without bound. In other words, the energy required to accelerate an object with mass to the speed of light becomes infinite. This is the fundamental reason why objects with mass cannot reach that speed. No physical process can supply an infinite amount of energy. This theoretical prediction is not merely a mathematical curiosity. It has been confirmed through decades of experiments in particle physics. Modern particle accelerators are capable of pushing tiny particles to speeds extremely close to the speed of light. Two well-known examples are CERN, the European Organization for Nuclear Research located near Geneva in Switzerland, and Fermilab, the Fermi National Accelerator Laboratory near Chicago in the United States. At these facilities, powerful electromagnetic fields are used to accelerate particles such as protons and electrons through enormous circular tunnels. The Large Hadron Collider at CERN, for instance, accelerates protons around a ring roughly 27 kilometers in circumference. As the protons circulate through the accelerator, they gain enormous amounts of energy. Yet something interesting happens as the energy increases. Even though the energy supplied to the particles grows dramatically, their speeds change only slightly. Protons inside the Large Hadron Collider move at about 99.999991% of the speed of light. That is incredibly fast, but it is still not equal to the speed of light. Adding more energy makes the particles more energetic, but their velocities approach the speed of light asymptotically, meaning they get closer and closer without ever reaching it. This behavior matches the predictions of special relativity perfectly. Another practical challenge arises in these accelerators because of a phenomenon called synchrotron radiation. When charged particles move along curved paths at extremely high speeds, they emit electromagnetic radiation. This radiation carries energy away from the particles. The faster the particles move and the tighter the curvature of their path, the stronger this radiation becomes. In large circular accelerators, enormous engineering effort goes into compensating for these energy losses. Powerful radio frequency cavities continuously supply energy to the particles in order to maintain their speed. For lighter particles, such as electrons, synchrotron radiation becomes particularly intense. This is one reason why some modern accelerators use straight linear designs instead of circular ones. The radiation itself is actually useful in other contexts. Dedicated synchrotron facilities produce extremely bright beams of light used for studying the structure of materials, biological molecules, and chemical reactions. Still, the presence of synchrotron radiation highlights a practical limitation of accelerating particles to extremely high energies. Even if engineers could build ever larger machines, the fundamental relativistic energy barrier would remain. The closer an object comes to the speed of light, the more stubborn the universe becomes about allowing further acceleration. The theoretical foundations for these energy relationships were explored in detail by physicists such as Lev Landau and Evgeny Lifshitz, whose influential textbooks helped formalize relativistic mechanics during the 20th century. Their work clarified how mass, energy, and momentum behave within the framework of special relativity. The result is a consistent and elegant picture. Objects with mass can approach the speed of light but never reach it. Massless particles, such as photons, always travel at that speed. And the closer anything comes to the cosmic speed limit, the more energy the universe demands in order to push it further. In this sense, the speed of light acts like a horizon. No wall physically blocks the path. No invisible force pushes objects back. Instead, the mathematics of energy quietly stretches the effort required to cross the boundary toward infinity. No matter how determined the traveller might be, the universe simply asks for more energy than can ever be provided, and so the limit remains intact. Up to this point, the story has focused largely on objects that cannot reach the speed of light. Spacecraft, Particles with mass and everyday objects all encounter the same barrier. The closer they approach light speed, the more energy is required to push them further. Yet the universe does contain things that move exactly at that speed. Light itself is the most familiar example, but modern physics has revealed that light is not simply a continuous wave spreading through space. Instead, it is made of tiny packets of energy known as photons. Photons are the fundamental particles of light. They carry electromagnetic energy, and they are responsible for everything from sunlight warming the Earth to the signals travelling through fibre optic cables beneath oceans. The detailed behaviour of photons is described by a theory known as quantum electrodynamics, often abbreviated as QED. Quantum electrodynamics combines the principles of quantum mechanics with the electromagnetic theory first described by James Clerk Maxwell. It explains how charged particles interact by exchanging photons, and it provides incredibly accurate predictions about the behaviour of light and matter. The development of quantum electrodynamics during the 20th century was a remarkable collaborative effort involving several physicists. Among the most influential contributors were Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Each of these scientists developed mathematical techniques that allowed the interactions between particles and photons to be calculated with extraordinary precision. Their work showed that even subtle quantum effects could be predicted accurately using the framework of quantum electrodynamics. In recognition of these achievements, Feynman, Schwinger, and Tominaga shared the Nobel Prize in Physics in the year 1965. One of the remarkable features of photons is that they have no rest mass. If you could somehow catch a photon and bring it to a halt, you would not find any mass associated with it. In fact, a photon cannot be brought to rest at all. Photons always travel at the speed of light in empty space. This behaviour is not a coincidence. It arises directly from the equations describing mass, energy, and motion in relativity. When an object has mass, the relativistic energy relationship ensures that accelerating it to the speed of light would require infinite energy. But if an object has no mass, the situation changes completely. For a massless particle, the only consistent speed allowed by the equations of relativity is the speed of light itself. In other words, massless particles must always move at that speed. They cannot move slower, and they cannot move faster. They simply exist on the boundary defined by the light cone in spacetime. Understanding why some particles have mass while others do not became one of the central questions of modern particle physics. For many years, physicists suspected that mass might arise through interactions with a deeper field permeating the universe. This idea eventually led to the proposal of the Higgs mechanism, named after the British physicist Peter Higgs. In the 1960s, Higgs and several other researchers suggested that empty space might contain a field that interacts with certain particles. When particles interact with this field, they acquire mass. Particles that do not interact with the field remain massless. The Higgs mechanism became a cornerstone of what physicists now call the Standard Model of particle physics, which describes the fundamental particles and forces known today. The field associated with this mechanism is known as the Higgs field, and the particle associated with it is the Higgs boson. For decades, the Higgs boson remained a theoretical prediction. But in the year 2012, scientists working at the Large Hadron Collider at CERN announced the discovery of a particle consistent with the Higgs boson. This discovery confirmed an essential piece of the modern understanding of mass. Within this framework, photons do not interact with the Higgs field in the way many other particles do. As a result, they remain massless. Because they have no mass, the relativistic equations naturally place them on the surface of the light cone, travelling through space-time at exactly the speed of light. Other massless particles exist as well, although they are less familiar than photons. For example, the particles that carry the strong nuclear force inside atomic nuclei, called gluons, are also believed to be massless in the Standard Model. However, gluons are confined inside protons and neutrons due to the nature of the strong force, so they do not travel freely across space in the way photons do. The photon therefore remains the most familiar example of a particle moving at light speed across the universe. Every time sunlight reaches Earth after its 8-minute journey from the Sun, billions upon billions of photons arrive simultaneously. Each one has travelled through space at precisely the same cosmic speed limit. These photons carry energy and information about distant stars and galaxies. They allow astronomers to study objects billions of light years away, revealing the history of the universe itself. Because photons always move at the speed of light, They experience space-time in a way that is difficult to describe using ordinary language. According to relativity, a particle travelling at the speed of light does not experience time in the same way massive objects do. From the photon's perspective, the journey across space occurs without the passage of time. While this idea stretches the imagination, it highlights once again how deeply the speed of light is woven into the structure of space-time. Massive objects approach the speed of light but never quite reach it. Massless particles exist exactly at that speed from the moment they are created. The universe therefore separates motion into two distinct categories. Objects with mass move slower than light. Objects without mass move at light speed. And between these two realms lies the cosmic boundary that relativity so elegantly explains. One of the deepest reasons the universe seems to enforce a speed limit has nothing to do with engines, rockets, or even energy. It has to do with cause and effect. In physics, the concept of causality is very simple at its core. A cause must occur before its effect. An event can influence something that happens later, but not something that has already happened. If you flip a light switch, the room becomes illuminated afterward. The illumination does not occur before the switch is pressed. If you throw a ball, the ball begins moving after your hand pushes it forward, not before. This ordering of events feels so natural that we rarely think about it. Yet maintaining this order turns out to be deeply connected to the speed of light. In Einstein's theory of relativity, information cannot travel faster than light. Any signal that carries information, energy, or influence must remain within the light cone structure of spacetime. This restriction ensures that causes always remain in the past of their effects. But if faster than light signals were possible, something very strange would happen. The ordering of the events could become scrambled. To see why, physicists sometimes explore thought experiments involving observers moving relative to one another. Imagine two spacecraft drifting far apart in deep space. Each ship is moving at a high speed relative to the other. Now suppose one spacecraft sends a message to the other, using a hypothetical, faster-than-light transmitter. From the perspective of the sender, the signal travels instantly or nearly instantly across space. However, because of the way time and space transform between moving reference frames, the receiving spacecraft might observe the signal arriving before it was sent. If the second spacecraft then sends a reply using the same faster-than-light method, it is possible for the reply to arrive back at the original spacecraft before the first message was transmitted. In effect, the response could arrive before the question. This type of scenario is sometimes called a causal paradox. In its most playful version, it resembles a time travel puzzle. Imagine sending a message to the past telling yourself not to send the original message. If the warning succeeds, the message is never sent. But if the message is never sent, the warning could not have been received in the first place. The logic loops around in a circle. While such paradoxes may sound like material for science fiction, they arise naturally when faster-than-light communication is combined with the relativistic structure of space-time. Special relativity does not merely limit speeds for practical reasons. It prevents situations where cause and effect could be reversed. The light cone structure ensures that information flows consistently forward through time. Every event that influences another must lie within its past light cone. Physicists became increasingly aware of this connection during the 20th century as they explored more exotic solutions to Einstein's equations. One particularly intriguing example came from the mathematician Kurt Gödel. In the year 1949, Gödel discovered a solution to Einstein's equations of general relativity describing a universe that rotates as a whole. In this rotating universe model, the geometry of spacetime becomes twisted in a way that allows certain paths through spacetime to loop back on themselves. These paths are called closed time-like curves. If an object followed such a path, it could theoretically travel through spacetime and return to an earlier moment in its own history. Gödel's solution demonstrated that Einstein's equations alone do not automatically forbid every form of time travel. However, the Gödel universe does not resemble the universe we observe. It requires conditions that appear incompatible with astronomical evidence, such as a global rotation of spacetime on cosmic scales. Nevertheless, Gödel's discovery revealed that the relationship between relativity and causality was more subtle than many physicists had initially assumed. The possibility of closed time-like curves raised a profound question. Why does our universe appear to avoid these paradoxical situations? One proposed answer came from the British physicist Stephen Hawking. Hawking suggested what he called the chronology protection conjecture. This idea proposes that the laws of physics prevent the formation of time loops that would violate causality. In other words, the universe might possess built-in mechanisms that protect the orderly sequence of cause and effect. Hawking famously joked that the absence of visitors from the future could be considered weak experimental evidence for this principle. Although that remark was delivered with humour, the underlying idea reflects a serious question in theoretical physics. Many physicists suspect that deeper laws of nature, possibly involving quantum gravity, forbid situations where time paradoxes could occur. Within the framework of special relativity, the speed of light already plays a central role in maintaining this consistency. By limiting the speed at which information can travel, relativity preserves the causal structure of space-time. Events remain linked in a consistent order. Signals move forward through time from causes to effects. No observer can send a message into their own past. The light speed limit therefore acts as more than just a restriction on motion. It acts as a guardian of logical consistency in the universe. Without that limit, the orderly progression of events could break down. Messages might arrive before they were sent. Effects might appear before causes. The familiar structure of time itself would become unstable. Instead, the universe appears to enforce a clear rule. Information travels no faster than light. Because of that rule, the flow of cause and effect remains intact across the vast expanse of space-time, and the story of the cosmos unfolds in a sequence that always moves forward. When physicists talk about the speed of light as a universal limit, they are not only referring to the motion of objects. The restriction also applies to something more subtle and equally important: information. Information is the physical content carried by signals. It is what allows a message to travel from one place to another, what allows a measurement to be communicated, and what allows events in one region of the universe to influence events somewhere else. At first glance, information might seem like an abstract concept, belonging mainly to mathematics or computer science. But during the 20th century, scientists began to understand that information has deep connections to the physical world. One of the key figures in this realization was the American mathematician and engineer Claude Shannon. In the year 1948, Shannon published a groundbreaking paper titled A Mathematical Theory of Communication. In this work, he introduced what is now known as information theory. Shannon's theory provided a precise mathematical way to describe how information is transmitted, encoded and decoded. It defined the concept of a bit, the basic unit of information, representing a choice between two possible alternatives. Information theory made it possible to calculate how efficiently messages could be transmitted through communication channels such as telegraph wires, radio signals, and eventually digital networks. Although Shannon's work focused primarily on engineering problems, it revealed something deeper. Information is not just an abstract pattern. It is something that must be carried by physical systems. Every message requires a physical medium. Radio waves carry signals through space. Electrical currents transmit information through wires. Even written text requires ink on paper or patterns of light on a screen. Once information is recognized as something physical, it must obey the laws of physics. That realization led to another important insight from the physicist Rolf Landauer. Landauer worked at the IBM research laboratories in the 20th century, and he explored the relationship between information and thermodynamics. His key insight is often summarized in a statement now called Landauer's principle. Landauer showed that erasing information from a physical system requires energy. When a bit of information is erased, a minimum amount of heat must be released into the environment. This idea connected information processing directly to the laws of thermodynamics. In other words, information is not free from physical constraints. Storing it, moving it, or destroying it always involves real physical processes. Once information becomes part of physics, the universal speed limit naturally applies to it. Any signal carrying usable information must travel no faster than light. This principle becomes particularly interesting when we consider one of the most mysterious features of quantum mechanics: quantum entanglement. Quantum entanglement occurs when two particles become linked in such a way that their properties remain correlated even when separated by enormous distances. If two particles are entangled, measuring the state of one particle instantly determines the state of the other. For example, two entangled photons might share a property such as polarization. If one photon is measured and found to have a certain polarization, the other photon will immediately display the corresponding value when measured. At first glance, this behavior seems to suggest that information might travel faster than light. After all, the measurement of one particle appears to influence the other instantly, even if the particles are separated by vast distances. Albert Einstein himself found this phenomenon deeply unsettling. He famously referred to it as spooky action at a distance. Over time, experiments have repeatedly confirmed that entangled particles do exhibit correlations stronger than any classical explanation would allow. Physicists have conducted increasingly precise tests of these correlations using photons, atoms, and other quantum systems. Among the researchers who have explored the implications of quantum entanglement is the Swiss physicist Nicholas Gysin, who has performed experiments investigating quantum non-locality and the limits of information transfer. Despite the remarkable correlations observed in entangled systems, a crucial rule remains intact. This rule is known as the no-signaling principle. The no-signaling principle states that entanglement cannot be used to send usable information faster than light. Although the measurement outcomes of entangled particles are correlated, those outcomes are fundamentally random. When one observer measures an entangled particle, the result appears unpredictable. Only when the results from both observers are later compared does the correlation become visible. But comparing those results requires ordinary communication, and ordinary communication cannot exceed the speed of light. Because of this requirement, entanglement cannot be used to send messages instantly across space. Even though the correlations appear immediate, they do not allow information to travel faster than the cosmic speed limit. This distinction is subtle, but extremely important. Quantum mechanics allows correlations that seem instantaneous, yet it preserves the fundamental restriction imposed by relativity. Signals carrying usable information remain confined within the light cone structure of space-time. This delicate balance between quantum mechanics and relativity has been confirmed through decades of experimental research conducted by laboratories around the world. Scientists have tested entanglement across optical fibers, between satellites and ground stations, and even across distances of hundreds of kilometers. In every case, the same conclusion emerges. Quantum entanglement is real and deeply mysterious, but it does not allow information to outrun light. The universe appears to maintain a consistent rule. No matter how exotic the phenomenon, no matter how strange the behavior of quantum systems, signals capable of transmitting information remain limited by the speed of light, and so the cosmic speed limit extends beyond matter and energy. It governs the very flow of information across the universe itself. Even though the laws of physics forbid any object with mass from exceeding the speed of light, astronomers occasionally encounter observations that seem, at first glance, to contradict this rule. When telescopes observe certain distant galaxies, especially extremely energetic objects known as quasars, they sometimes detect jets of material that appear to move faster than light. This phenomenon is known as apparent superluminal motion. The word superluminal simply means faster than light. To anyone encountering the term for the first time, it might sound like a dramatic violation of relativity. After all, if something in the universe truly travelled faster than light, it would undermine the entire structure of space-time described by Einstein's theory. Yet careful analysis shows that these observations do not break the cosmic speed limit. Instead, they reveal a fascinating optical illusion, created by geometry, distance, and the finite speed of light itself. Quasars are among the most luminous objects in the universe. They are powered by supermassive black holes at the centers of distant galaxies. As matter spirals toward these black holes, enormous amounts of energy are released. In many cases, this process produces narrow beams of particles that shoot outward from the region around the black hole. These beams are known as relativistic jets. The particles within these jets travel at speeds extremely close to the speed of light. Because these jets can extend for thousands of light years, astronomers can sometimes observe bright knots of material moving along the jet over time. By comparing images taken months or years apart, it becomes possible to track the apparent motion of these features, and occasionally, the calculations suggest that the knots are moving across the sky faster than light itself. The puzzle of apparent superluminal motion attracted considerable attention during the 1960s and 1970s. One of the scientists who helped clarify the explanation was the British astrophysicist Martin Rees. Rees demonstrated that the apparent violation arises from the combination of very high speeds and the angle at which the jet is oriented relative to Earth. To understand how this illusion works, Imagine a jet of particles travelling at a speed extremely close to the speed of light. Instead of moving directly across our line of sight, the jet is pointed almost toward us. Because the particles are moving nearly in our direction, the light they emit at different moments does not travel the same distance to reach Earth. Light emitted later in the jet's motion has a shorter distance to travel than light emitted earlier. This difference in travel time compresses the apparent interval between observations. As a result, when astronomers compare images taken over time, the apparent motion projected across the sky can seem faster than light. The effect is purely geometric. No individual particle actually exceeds the speed of light. Instead, the combination of high velocity and viewing angle creates the illusion of superluminal motion. The mathematics describing this phenomenon shows that the apparent transverse speed across the sky can exceed the speed of light even when the true velocity remains slightly below it. One of the key ingredients in these observations is a process called relativistic beaming. When particles move at speeds close to the speed of light, the radiation they emit becomes concentrated in the direction of their motion. This effect arises from the relativistic transformation of angles and intensities. In practical terms, the radiation from the jet becomes strongly focused into a narrow cone pointing forward. If that cone happens to point toward Earth, the jet appears dramatically brighter than it would otherwise. Active galactic nuclei, which are the energetic cores of certain galaxies containing supermassive black holes, often produce such relativistic jets. When one of these jets points roughly toward Earth, the object can appear extraordinarily bright and variable. Astronomers call such objects blazars, a type of active galactic nucleus, where relativistic beaming strongly enhances the observed emission. Studying the apparent motion within these jets requires extremely precise observations. One of the most powerful tools used for this purpose is a technique called Very Long Baseline Interferometry, often abbreviated as VLBI. In this method, radio telescopes separated by thousands of kilometers across the Earth operate together as a single enormous instrument. By combining signals from telescopes located on different continents, astronomers can achieve angular resolutions equivalent to a telescope thousands of kilometers wide. This extraordinary precision allows researchers to measure the positions of radio sources with astonishing accuracy. Using very long baseline interferometry, astronomers have tracked the motion of jets emerging from quasars and active galactic nuclei over periods of many years. These observations repeatedly reveal features moving outward along the jets with apparent speeds greater than the speed of light. Yet when the geometry of the system is taken into account, the results fit perfectly within the framework of relativity. The particles themselves remain slightly below light speed. The illusion arises because of the way light from different points along the jet reaches Earth at slightly different times. In a sense, the finite speed of light is responsible for creating the illusion of exceeding that same speed. It is a reminder that astronomical observations often involve subtle effects that only become clear when the geometry of space-time is carefully considered. Far from violating relativity, apparent superluminal motion actually provides strong evidence for it. The observations confirm that jets from quasars and active galactic nuclei contain particles moving at velocities extremely close to the speed of light, just as the theory predicts. And they demonstrate once again that the cosmic speed limit remains intact. Even in the most energetic regions of the universe, where black holes launch jets across thousands of light years, the rules of space-time still apply. Nothing truly outruns light itself. Although relativity places a strict limit on the speed of objects with mass, physicists have occasionally explored more unusual possibilities. One of the most famous speculative ideas involves hypothetical particles known as tachyons. The concept of tachyons was explored in the 1960s by the American physicist Gerald Feinberg. Feinberg was interested in understanding whether relativity itself might allow the existence of particles that always move faster than light. At first, this may sound impossible. After all, relativity tells us that accelerating an object with mass to the speed of light requires infinite energy. But Feinberg noticed something intriguing when examining the relativistic energy equations. The equations describing energy and momentum contain the speed of light as a boundary between two different regimes of motion. Particles with ordinary mass move slower than light and can approach that boundary, but never cross it. Feinberg asked a provocative question. What if there were particles that already existed on the other side of that boundary? Instead of accelerating up to the speed of light from below, Such particles would always move faster than light from the moment they were created. These hypothetical particles were given the name tachyons, derived from a Greek word meaning swift. In the mathematical framework explored by Feinberg, tachyons would possess unusual properties. Their energy would behave differently from ordinary particles. In fact, according to the equations, adding energy to a tachyon would cause it to slow down rather than speed up. Even more strangely, if a tachyon were somehow to lose energy, its velocity would increase further beyond the speed of light. These unusual characteristics arise because the relativistic equations involve the square of the velocity divided by the square of the speed of light. For particles travelling faster than light, the mathematical expression behaves in ways that feel unfamiliar. One way to describe tachyons mathematically is to say they would possess an imaginary rest mass. This phrase does not mean the particles are imaginary in the everyday sense of being fictional. Instead, it refers to a mathematical quantity that arises when the square root of a negative number appears in the equations. While the mathematics allows such solutions, interpreting them physically is far more difficult. One major challenge is that tachyons would almost certainly create problems for causality. Because faster-than-light motion allows signals to travel outside the light cone of spacetime, tachyons could potentially send information backward in time for some observers. As discussed earlier, this leads to paradoxes involving cause and effect. These difficulties make many physicists skeptical that tachyons exist as real particles in nature. Even so, the idea of tachyons occasionally appears in more advanced theoretical frameworks. In quantum field theory, for example, physicists sometimes encounter something called a tachyonic field. A tachyonic field does not necessarily represent a particle moving faster than light. Instead, it often indicates that a particular configuration of a field is unstable. When a tachyonic mass term appears in the equations describing a field, it usually means the system is sitting in an unstable state, somewhat like a ball balanced on the top of a hill. The presence of the tachyonic term signals that the system will evolve toward a more stable configuration. A famous example of this behavior occurs in the Higgs mechanism, where the Higgs field initially appears with a tachyonic mass term in the equations. Rather than implying faster-than-light particles, this feature indicates that the field will settle into a stable configuration with a non-zero value throughout space. In that stable state, particles interacting with the field acquire mass. Another context where tachyonic modes appear is string theory, a theoretical framework attempting to unify quantum mechanics with gravity. In some early versions of string theory, the mathematical description of vibrating strings produced tachyonic states. These states signaled that the particular formulation of the theory was unstable. Researchers including Edward Witten and others worked on developing more sophisticated versions of string theory, where these tachyonic instabilities could be removed or interpreted in more meaningful ways. Within these theories, the appearance of tachyonic modes often serves as a warning sign that the model needs to be refined. Beyond string theory, modern theoretical physics also explores deep connections between gravity and quantum field theories. One of the most influential ideas in this area is the ADS-CFT correspondence, proposed by the Argentine physicist Juan Maldacena in the late 1990s. This framework suggests that certain gravitational systems in higher dimensional spacetimes can be mathematically equivalent to quantum field theories defined on lower dimensional boundaries. Although tachyonic fields sometimes appear within these mathematical structures, they do not necessarily correspond to faster-than-light particles travelling through ordinary spacetime. Instead, they often represent instabilities or transitions between different physical states within the theory. Despite the fascinating mathematics surrounding tachyons, no experiment has ever detected a particle moving faster than light. High-energy particle accelerators, cosmic ray detectors, and astronomical observations have all searched for signs of superluminal particles without success. Every confirmed particle discovered so far behaves exactly as relativity predicts. Objects with mass travel slower than light. Massless particles travel at the speed of light, and nothing has been observed that consistently exceeds that boundary. For this reason, tachyons remain a speculative idea. They serve as useful tools in mathematical explorations of quantum fields and theoretical models, but they have not been confirmed as physical entities. Still, the study of such possibilities plays an important role in physics. By exploring the limits of our theories, scientists learn more about the structure of the laws governing the universe. Sometimes these explorations reveal unexpected insights. and sometimes they simply reinforce a principle that continues to hold firm. So far, every reliable experiment continues to point toward the same conclusion. The cosmic speed limit remains intact. Even though relativity imposes a strict limit on the speed at which objects can move through spacetime, physicists have occasionally wondered whether there might be ways to work around that restriction without technically breaking it. The key idea behind many of these proposals is subtle but important. Perhaps nothing can move faster than light through spacetime, but what if spacetime itself could be reshaped? This possibility emerges from Einstein's later theory of general relativity, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. In this theory, massive objects such as stars and planets bend the geometry of spacetime around them. Objects moving through that curved geometry follow paths determined by the shape of spacetime itself. If spacetime can be curved, stretched, or twisted, then in principle it might be possible to engineer shortcuts through the cosmic landscape. One of the most famous ideas along these lines involves structures known as wormholes. The term wormhole was popularized by the American theoretical physicist John Archibald Wheeler, who studied the topology of spacetime during the 20th century. Wheeler imagined spacetime as something that might contain tunnels connecting distant regions. To visualize the idea, imagine a sheet of paper representing the surface of space. 2 points on the sheet might be far apart if you travel along the surface. But if the sheet could somehow be folded so those 2 points touch, a tunnel passing through the fold would create a much shorter path between them. A wormhole is the spacetime equivalent of that tunnel. In mathematical terms, a wormhole connects two separate regions of spacetime through a shortcut that bypasses the ordinary distance between them. Early theoretical discussions of wormholes appeared in the 1930s, when Albert Einstein and Nathan Rosen studied solutions to Einstein's gravitational equations that connected two black holes through what later became known as an Einstein-Rosen bridge. However, those early solutions were not stable or traversable. They would collapse too quickly for anything to travel through them. Decades later, physicists began asking whether stable wormholes might exist in principle. One of the leading figures in this work was the American theoretical physicist Kip Thorne, working at the California Institute of Technology. In the 1980s, Thorne and his collaborators studied the possibility of traversable wormholes, structures that could remain open long enough for matter or signals to pass through them. Their calculations showed that such wormholes might be possible if spacetime was supported by a type of material with very unusual properties. This material would need to possess negative energy density. Ordinary matter always has positive energy density. Negative energy sounds exotic, but it does appear in certain quantum phenomena. One example is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in the year 1948. The Casimir effect occurs when two extremely smooth metal plates are placed very close together in a vacuum. Quantum fluctuations in the vacuum create a small pressure difference between the inside and outside of the plates. The result is a tiny attractive force pulling the plates together. This effect can be interpreted as producing a region of negative energy density between the plates relative to the surrounding space. Although the Casimir effect has been measured experimentally, the amount of negative energy involved is extremely small. Theoretical wormholes would require vastly larger quantities of negative energy to remain stable. Despite this challenge, the concept of manipulating spacetime itself has continued to inspire new ideas. One of the most famous proposals appeared in the year 1994 when the Mexican physicist Miguel Alcubierre introduced a theoretical model now known as the Alcubierre warp drive. Alcubierre realized that Einstein's equations allow solutions in which spacetime is compressed in front of a spacecraft and expanded behind it. Inside this region of distorted spacetime, the spacecraft itself would remain stationary, relative to the surrounding bubble, but the bubble could move through spacetime at an effective speed greater than light. The key point is that the spacecraft would not be traveling faster than light through its local region of spacetime. Instead, spacetime itself would be moving. This idea resembles a surfer riding a wave. The surfer moves forward not by swimming through the water faster than the wave, but by being carried along with it. In Alcubierre's model, the wave would be a distortion in spacetime geometry. Mathematically, the concept is consistent with the equations of general relativity. However, the physical requirements are enormous. Early calculations suggested that creating such a warp bubble might require energy comparable to the mass energy of an entire planet or even a star. Later theoretical refinements reduced these estimates somewhat, but the required energy remains far beyond anything humanity could realistically produce. Another difficulty arises from the same issue encountered with traversable wormholes. The warp drive solution requires regions of negative energy density. Because negative energy appears only in tiny quantities in known quantum phenomena, it remains unclear whether large-scale spacetime engineering is physically possible. Nevertheless, some researchers continue exploring these ideas. Among them is Harold White, an engineer and physicist who has investigated theoretical modifications of the Alcubierre concept, while working with research groups associated with space propulsion studies. White and others have explored whether alternative geometries might reduce the energy requirements for warp drive solutions. So far, these investigations remain speculative and theoretical. No experiment has demonstrated the creation of warp bubbles or stable wormholes. Still, the fact that such ideas emerge from the equations of general relativity is itself fascinating. Einstein's theory does not merely describe gravity. It provides a mathematical framework in which spacetime can be stretched, curved, and connected in unexpected ways. Whether those possibilities can ever be realized in practice remains unknown. For now, the cosmic speed limit remains firmly in place. Nothing with mass can outrun light through ordinary spacetime, yet the exploration of wormholes, warp drives, and other forms of spacetime engineering reminds us that the geometry of the universe may still hold surprises waiting to be understood. For most of this journey, the cosmic speed limit has appeared as a strict boundary. Nothing with mass can accelerate past the speed of light, and signals carrying information must remain within the structure defined by spacetime. Yet there is one situation in which distances in the universe can grow faster than light. This might sound surprising at first. If relativity forbids faster than light motion, how could anything in the universe move away faster than that limit? The answer lies in a subtle but crucial distinction. Objects cannot move faster than light through space, but space itself can expand. The discovery that the universe is expanding began during the early 20th century, when physicists started applying Einstein's theory of general relativity to the cosmos as a whole. One of the first people to realize that Einstein's equations allowed an expanding universe was the Russian mathematician and physicist Alexander Friedmann. In the year 1922, Friedmann published solutions to Einstein's gravitational equations, describing a universe whose size changes over time. His equations showed that spacetime itself could stretch or contract depending on the density of matter and energy it contained. These solutions were purely mathematical at first, and many scientists remained uncertain whether they described the real universe. A few years later, the Belgian physicist and priest Georges Lemaitre independently reached similar conclusions. Lemaitre studied the same equations and recognized that they naturally described a universe that began from a dense, compact state and then expanded over time. Lemaitre proposed that galaxies should be moving away from one another as space itself stretches. At the time, this idea seemed radical. Most astronomers believed the universe was static and unchanging on large scales. That view began to shift when observational evidence arrived from the work of the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California during the 1920s, Hubble studied distant galaxies using one of the most powerful telescopes of the era. By examining the spectra of these galaxies, he noticed a consistent pattern. The light from distant galaxies was shifted toward longer wavelengths, a phenomenon known as redshift. This redshift occurs when a light source moves away from an observer. The wavelengths of the light stretch slightly as the source recedes. Hubble discovered that the farther away a galaxy was, the greater its redshift appeared to be. This relationship became known as Hubble's law. In simple terms, the law states that galaxies are moving away from us at speeds proportional to their distance. The farther a galaxy lies from Earth, the faster it appears to be receding. The most natural explanation for this pattern is that the universe itself is expanding. Rather than galaxies moving through static space like particles flying through a room, the distances between galaxies are increasing because space itself is stretching. A helpful analogy involves imagining dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart even though they remain fixed on the surface. Each dot sees every other dot moving away. The same principle applies to galaxies embedded within the expanding fabric of spacetime. This expansion leads to an interesting consequence. Because the expansion rate increases with distance, galaxies far enough away can appear to recede faster than the speed of light. This does not violate relativity because those galaxies are not travelling through space faster than light. Instead, the space between us and those galaxies is expanding. The galaxies remain locally stationary relative to their surrounding spacetime, while the overall geometry of the universe changes. In this sense, the cosmic speed limit still applies. Nothing locally outruns light. The expansion of space simply carries distant galaxies away as the universe grows larger. An even more dramatic episode of expansion is believed to have occurred during the earliest moments of cosmic history. This period is known as cosmic inflation. The idea of inflation was first proposed in the early 1980s by the American physicist Alan Guth. Guth suggested that shortly after the birth of the universe, space-time underwent an extremely rapid burst of expansion. During this brief interval, the universe may have grown by an enormous factor in a fraction of a second. Later work by physicists such as Andrei Linde developed more detailed models of inflation, describing how quantum fields could drive this explosive expansion. During inflation, regions of space could have expanded away from one another far faster than the speed of light. Yet again, this does not violate relativity because the motion involves the expansion of space-time itself rather than objects moving through space. The distinction may feel subtle, but it is essential. Relativity limits how fast matter, energy, and information can travel within space-time. It does not forbid the geometry of space-time from evolving. Observations of the universe today strongly support the idea that cosmic expansion continues. Measurements of distant supernovae, the cosmic microwave background radiation, and large-scale galaxy surveys all confirm that the universe has been expanding for billions of years. Even more intriguing, the expansion appears to be accelerating due to a mysterious component known as dark energy. As a result, extremely distant galaxies are being carried away faster and faster as space continues to stretch. Some galaxies are now receding so rapidly that light emitted today will never reach Earth. They lie beyond what cosmologists call the cosmic event horizon, a boundary determined by the expansion of space-time itself, and so the universe presents us with an elegant picture. Within any local region of space-time, the speed of light remains the ultimate limit. Nothing can outrun it. Yet on the grandest scales imaginable, the universe itself can grow and stretch in ways that carry entire galaxies apart, faster than light could travel between them. It is a reminder that the laws of physics are subtle, and sometimes the universe finds ways to expand without ever breaking its own rules. As the journey through physics unfolds, one pattern becomes increasingly clear. The speed of light is not merely a detail about how fast beams of light travel through space. Instead, it appears repeatedly across many different areas of physics, quietly shaping the structure of the laws that describe the universe. In electromagnetism, the speed of light emerges naturally from the properties of empty space itself. Maxwell's equations reveal that electric and magnetic fields can propagate through space as waves, and the speed of those waves is determined by two fundamental properties of the vacuum: electric permittivity and magnetic permeability. Combine those properties, and the resulting speed is exactly the speed of light. In relativity, the same constant appears again, not simply as the speed of a particular phenomenon, but as a structural feature of space-time. It sets the relationship between space and time in the geometry described by Minkowski spacetime. It determines the slope of light cones, the paths along which information and influence can travel, and it marks the boundary separating events that can affect one another from those that cannot. In particle physics, the speed of light governs how particles behave at extremely high energies. It appears in the relationship between energy and mass, in the equations describing relativistic momentum, and in the dynamics of fields that make up the Standard Model. Even the modern definition of distance in the International System of Units reflects this constant. Today, the meter is defined using the speed of light itself. Specifically, 1 meter is the distance light travels in a fraction of a second, equal to 1 divided by 299,792,458. This definition emphasizes that the speed of light is not merely measured, it is fundamental. Because it appears so frequently in physics, scientists have wondered whether it might belong to a deeper category of constants describing the universe. One particularly interesting type of constant is known as a dimensionless constant. Unlike quantities such as meters or seconds, dimensionless constants have no units. They are pure numbers that remain the same regardless of the measurement system used. One famous example is the fine structure constant, which describes the strength of the electromagnetic interaction between charged particles. The fine structure constant was studied extensively by the German physicist Arnold Sommerfeld, who extended early quantum theory to explain subtle details in atomic spectra. The value of this constant is approximately 1 divided by 137. Because dimensionless constants do not depend on units, many physicists believe they reveal deep features of the universe's structure. Some scientists have even wondered whether these constants might change slowly over cosmic time. The British physicist Paul Dirac explored this idea in the 1930s with his large numbers hypothesis. Dirac noticed intriguing numerical relationships between certain cosmic quantities and suggested that some physical constants might evolve as the universe ages. Later researchers, including cosmologist John D. Barrow, examined whether observational evidence might reveal tiny changes in fundamental constants across billions of years. So far, careful astronomical observations suggest that constants such as the speed of light and the fine structure constant remain extremely stable, but the question itself highlights how deeply these numbers are woven into our understanding of physics. Meanwhile, efforts to unify general relativity with quantum mechanics have led to new ideas about the nature of spacetime itself. One approach, known as loop quantum gravity, has been explored by physicists including the Italian researcher Carlo Rovelli. Loop quantum gravity proposes that spacetime may not be infinitely smooth at the smaller scales. Instead, it might consist of tiny discrete units, somewhat like the individual threads in a fabric. According to this view, spacetime could have a granular structure at extremely small distances, on the order of what physicists call the Planck scale. If this picture is correct, then the speed of light might reflect deeper constraints arising from the microscopic structure of spacetime. Another fascinating idea comes from the holographic principle, first proposed by the Dutch physicist Gerard de Hooft, and later developed further by the American physicist Leonard Susskind. The holographic principle suggests that the information contained within a region of space may actually be encoded on the boundary surrounding that region. In other words, the three-dimensional universe we experience might be described by information stored on a two-dimensional surface, somewhat like a hologram projecting a three-dimensional image. This concept emerged from studies of black holes and quantum gravity, where physicists discovered surprising relationships between information, entropy, and the surface area of event horizons. If the holographic principle is correct, then the speed of light may play a role in determining how information flows through this deeper informational structure of the universe. From this perspective, the cosmic speed limit may not simply restrict motion. It may define the maximum rate at which information can propagate through spacetime. The same constant that governs the motion of photons might also regulate the fundamental exchange of information across the universe. Viewed in this light, the speed of light becomes more than a property of electromagnetic radiation. It becomes a central parameter defining how the universe processes information, organizes causality, and structures spacetime. Across electromagnetism, relativity, quantum theory, and cosmology, the same number appears again and again: 299,792 kilometers per second. It governs the motion of particles, it defines the geometry of spacetime, it limits how quickly signals can travel, and it shapes the horizons of the observable universe itself. The deeper physicists explore the laws of nature, the more this constant appears not as a coincidence, but as a fundamental ingredient of reality, a quiet number that sits at the heart of the universe's design. And perhaps one day, a deeper theory will reveal why that number takes the value it does. Until then, the speed of light remains both a boundary and a clue, a limit that hints at the deeper architecture of the cosmos.